Mm. Size, okay. Right. Oh, it doesn't come out. Yeah, okay. So powertrain is also one of the most important parts or system in an electric vehicle. So firstly, I'd like to ask you a few target questions. So what is a powertrain? What is the meaning of powertrain?
I mean, the path from your source to your to how you drive it.
Yeah. The
It's
source,
power.
input, output. Yeah. Input is the battery, right?
Yeah.
Maybe the charger. Output is the wheel. And all these are powertrain. So the powertrain later, of course, is different from the gasoline car, right? Later on, we'll discuss the difference between these two. So later on, we say what part will be included. Obviously, include all the power component, most high power component in there, like the motor, driver, battery, that will be the powertrain, right? So, why the powertrain technology will be important, will be used in powertrain? How do we put them together? How powertrains are related to the powertrain? What kind of technology they mix together? Any comment? What's the thing? Yeah, question number 3. What is the powertronic like? How we use powertronic in this technology?
Just like we use switch relay.
Yeah. Switch relay motor. We need the inverter to join the SR motor, the charger, motor driver, they all powertronic. So that's why all this relate to so-called power conversion. We do convert the power from one stage to other stage, either from one voltage level to other voltage level or current to other current level. I will adjust the power, amount of power go to the output. So that's why we do a battery. The battery is basically energy storage, and then even the motor and driver, sometimes they power from AC, sometimes from DC, sometimes mixed mode. Then how we power them? So we release certain power from the battery. Battery DC power. Some motor will be AC power. Some motor may be DC. So we need to do some power conversion and control. So all these things will be highly related to how our power electronic to control them. So this is the content we're going to discuss for this lecture, including what's powertrain, what's the configuration in EV, and how we design them, the basic converter we're going to use, and future development, what we're going to have. So that's basically how we're going to cover here. So firstly, then the basic component for powertrain, we're including all the power component, like the related to motion and the power. So probably it must include the electric motor and also the battery system. The powertronic also related to how to do the power conversion. Sometimes we use the powertronic to invert the inverter to drive the motor. Of course, that is our powertrain. We may need to use power converter. For instance, if we use DC motor, we use DC joint, DC power converter to drive them. Or sometimes the battery voltage is not sufficient. We use DC converter to control the voltage because different level of the voltage. That will become also the powertrain configuration. So that's why we use DC converter to match different kind of power level for the vehicle. For instance, your motor inverter, we need about 400 volts to drive that. But now then we use DC plus 800. So we need to reduce voltage a little bit for the drive system. Or sometimes if the charger is only about the power point charger, level 1 charger, level 2 charger on board vehicle, you're only using 120 volts. But this voltage is not sufficient, good enough for the battery voltage. You need to step up the voltage. So you also need a DC-DC converter to increase the power level, increase the voltage from your power point, this main power point for your battery voltage. So somehow we need to convert the DC voltage. So that's also the function of DC converter. So of course, the inverter basically will be to control the motor torque and the speed. And we may also consider the charging system. Because for charging system, we use the two charging systems. One will be on-board charging. So that means for electric vehicle, you can plug in the 108 volt or maybe 200 volt high voltage for on-board charging to the vehicle. So that is mainly about the AC convert to DC to charge the vehicle. So the rectifier, the charger control inside vehicle. But that usually for low power. Of course, later on we also study about the DC charger, high power DC charger. But high power DC charger is not inside the vehicle, it's outside the vehicle, not part of the powertrain. And the vehicle may also have the transmission and drive. Although for EV, the transmission and drive are getting less and less demanding, we tend to use all electric. So, but still some vehicles still have certain amount of the mechanical transmission, not too heavy. And then we also have something called a drivetrain. Later on, I'll show you what's the meaning of drivetrain, something related to the motor. And then vehicle itself also have the vehicle control unit, VCU. VCU is something more like a car computer to control everything. Everything goes to the central computer to control all the motion, charging, temperature, sensor, and everything. So that's how the operation looks like. So now then, more importantly, we have been working on ICE vehicle. So nice to see the comparison between ICE and EV. So the comparison are quite standard. And I think you can all draw this table easily. So for instance, one of the power source, and power source in here is to drive the motor power source or to drive the mechanical power source, ICE or the motor. The fuel, of course, the electricity or the gasoline or diesel, the energy conversion, we are mainly from fuel to mechanical. And then for the motor, of course, from electrical energy to mechanical energy, that's a motor. The powertrain component in here, you can see that we have, my mouse here cannot show on there anyway. So the mechanical part, we have the fuel tank, transmission, and engine, and that's quite normal. But for power component here, we got motor, inverter, and battery pack system. The efficiency is also quite important. ICE conversion, we don't have high efficiency, usually 10 to 25, not really promising. That's why we don't like gasoline car. But however, for electric vehicle system, basically at least 70%, or all vehicle at 96. 96 means from the input power electrical to the motor, that is 96. That already really good because we got charger, we missing some energy, missing some efficiency, and also the battery input output missing some efficiency, the inverter, and also the motor, each part will losing a little bit of percentage. Eventually, for good electric vehicle, we're able to maintain 96% for really good design. But most of them may be 95, 94, it's not surprising. So overall efficiency performance will be can reach 19 something. That will be a few times better than gasoline car. So you can see here roughly about 4 times, maybe 3 times of the performance difference. But although here you look like 3 to 4 times, but actually the vehicle can perform at least 5 times in energy performance, mainly because of power regeneration. The gasoline vehicle cannot do any power regeneration. When the vehicle going down the hill, then we got power regeneration. Then that's why we are able to recover more energy, can save more energy. For the maintenance, I think you all know that gasoline vehicle, we do have a lot of maintenance every 6 months or every maybe 10,000 miles. We need to go there for the maintenance. They change this and change that, change the lubrication oil, change some brake pad. So these are not the work we need to do. But for electric, then you can see that we don't really need too much maintenance. I think if you buy an EV, go to Tesla, they say, no, you don't need any maintenance. You don't need to come. Why is that? Because the braking, we use electronic brake. We still have mechanical brake there, but we seldom use it. If you drive a vehicle, you know that you always press the gas pedal. You don't really need to press the brake. So that's why the mechanism there will be, you don't need to use the brake pad is there, but you seldom use it. So that means it doesn't get any wear and tear. And then, so that's why, and there's a low lubrication oil there. No lubrication, no hydraulic system. Only the motor. The motor, they use bearing. So that's why you don't need to worry too much about the lubrication maintenance. So torque, of course, then we know that motor we can able to provide instant torque, really direct instant torque. Whatever torque control profile, we can control electronically. But for ICE, firstly, torque will be delayed when you press the gas pedal. You need some time period to deliver the ICE, deliver the transmission system to the torque. And also the torque profile is not instantly, it's not direct torque control. So everything goes delayed. And then, so that's why, as I mentioned, two vehicles in the red line, one gasoline car, one is an electric. Of course, the electric vehicle go first. It's really quick, able to start and speed up. And then refuel time, that's one of the major issues, right? In a gas station, probably just a few minutes, 3 minutes is quite typical. But for EV, then you may need to maybe at least 30 minutes for Tesla. For some other vehicle, level, if you use level 2 charger, may take 1 day, level 1 take a few days. So that's the issue, right? But so that's why you can see that refuel will become a major issue for electric vehicle. But however, you go to fast charging outside, it costs you a lot of money. Fast charger, they will charge you at least 3 times compared to your home charging. Although you can enjoy 30-minute charging time, that's quite okay. I mean, you wait there for 30 minutes, compared to wait there for 5 minutes in a gas station, still really sensible. But you need to pay more. Yeah, I think if you own an EV, then you know that you need to pay at least 3 times more electricity charge. So electricity charge roughly about, say, 15 cents per kilowatt hour at home in Seattle. But maybe in here, it costs you about 40 cents. But however, when you go to supercharging station, they charge you more, 2 times or 3 times more, because they need to pay back the investment for the supercharger. So that's why in a way, you may not have too much financial benefit. You may have a zero emission benefit for the whole entire planet Earth, but you don't have your own pocket benefit because they charge you quite a lot of the money. Anyway, so driving range, of course, it all depends on battery. You put more battery there, then you can drive longer time. But however, in here, it depends on tank size as well. So the typical comparison. So here is the powertrain now, and also the so-called drivetrain. The whole thing here is the powertrain. But for the drivetrain, mainly we need to drive. That means the motor go to the wheel is the drivetrain. The whole thing is the power. Anything with the power we call powertrain. That's how we separate these two names. So you need to know the driver. What's the drivetrain? What's the powertrain? Like that. So that means the powertrain mainly consists all the power components: battery, charger, DC link, vehicle control unit, and drivetrain, which consists of this motion, the movement part. Anything can move, we call them the drivetrain. So like the motor, sometimes we do have the reduction gear. As I mentioned, the motor we tend to use high-speed motor. I feel 10,000, 20,000 RPM. But the wheel here only a few hundred RPM. We need some reduction gear. And then in here, just now we mentioned all the power components. So that's how the configuration look like. Okay, any question up to this point? Then if we try to compare the powertrain of two systems, then you can see that a single ICE vehicle usually only have single ICE, single internal combustion engine. I never see any gasoline car have two ICE. Probably no, only one ICE. Then they got one ICE, they convert the mechanical power to the wheel through a differential. But for electric car, it's different. We can use at least 1, 2, or 4 motors, depending on which vehicle design. Many vehicles in the market today, they use 2 motors. That's really much like a standard So that's why it's quite different. So for the steering, ICE usually we use so-called the Ackerman steering. That means conventional, the one you are using for your car is called Ackerman steering. When you steer it, then the wheel will have an angle, right? Some people call it angle steering, but actually we call it Ackerman steering. This Ackerman steering, like that. When you want to turn, these two angles not exactly equal to each other. Because when you want to do the steering, then you can see that the steering radius for the interior for near side and outer side are different steering radius, different turning radius. So these two angles are different. So Ackerman are using special calculation, mechanical calculation, so that when you do the steering, they already are accommodate for this turning radius requirement to adjust your turning angle. So that's quite clever. Actually, go to the website to search for Ackerman. So now then, this Ackerman steering already really mature. All the vehicles are using it. Then go back to electric vehicle. Then we can either use Ackerman steering, or we can use differential as well. We can put two motor, have differential speed. We also control the differential changing of the turning. So that's also quite common. Of course, the fuel, we can see that you can use electricity or hydrogen for EV, but you have to use gasoline or diesel. Emission, you know that we have zero emission here. If you use purely renewable, then you can have zero emission. But this one is this typo here. It must have emission. It's not zero here. It must have some kind of the emission here. So this kind of vehicle, it must have some emission, mainly because the basic principle of the vehicle. So that's why. So next problem about the braking. Then you can see that this vehicle, of course, we don't have any gasoline braking. We have to use the mechanical braking, like frictional pad, like this brake is quite common. But for EV, we use power regeneration. So all the braking, we use the so-called the second quadrant or fourth quadrant method to control vehicle to brake. So in this case, the vehicle can save much more energy. Then for the braking age as well, we do need a lot of maintenance. We need to change the brake pad every maybe 2 years or so. But for electric vehicle, probably we don't need to change it. Maybe after 5 years, 6 years, you only need to change the brake pad. And also in the future or near future, all the autonomous vehicle, basically they all 100% based on electric vehicle. I don't think the IC vehicle can able to provide really good autonomous. Autonomous vehicle really difficult to work with the gasoline vehicle because we cannot control the motor properly. But for EV, you can control really well. So autonomous vehicle will be working really well for the electric vehicle. So you can see that basically two different between the powertrain. Then next is about the power conversion. Because we have different kind of the voltage and power level and energy storage, we do need to control how to control power from one stage to other stage. For EV, you can see that in here, we got many different kind of power conversion stage. Like in here, the main power, perhaps from our electricity from PG&E, then we convert this power into the battery using battery charging system. And then for the battery DC, we convert the DC voltage into the inverter AC to drive the motor or to drive the motor drive system. So the motor drive system. And then we also some power electronic. The power electronic, the control system, we usually about low voltage because microprocessor usually low voltage, maybe 12 volt, 5 volt. Then we have to use the battery voltage a few 100 volt to reduce the voltage to a few volt. That's another power conversion system. And then for the battery, we got so many battery cells there, so we need to control the battery. Control each of battery cell will working properly. Then we have some battery management. So that's how we can see for all the power conversion stage in an electric vehicle system. Then for the DC voltage, we are talking about the powertrain. So the DC voltage is a key component. We got DC power distribution for the vehicle. then the typical voltage can vary depending on your vehicle design. So for the old day, when we only have low power vehicle like the golf car or forklift, they're still electric vehicle. The voltage using 48 volt or 36 volt low voltage. For example, like if you have electric wheelchair is still an electric vehicle. The voltage only about 24 volt, maybe 12 volt. So that is also low power vehicle using 48 volt or less. And then for high power one, today it must be a few hundred volt, at least 150 to 500. Occasionally, we can see something maybe close to 100, but most of them today will be a few hundred volt. Why is that? Because you can see that the Japanese has been using this EV in the really beginning and maybe beginning of this century. At that time, they developed the EV are based on chargeable charging method. Chargeable. You can see the chargeable. I think you heard about that. The Japanese are using standard charging called the chargeable. CHEDMOV, this kind of spelling. Chargeable charging are based on 150 volt or above. So that means you can see that most of the system during the time for high power vehicle, they start from 150. During that time, already very high power, but today we go for 800 volt anyway. So now the large vehicle like the buses or high performance vehicle, they go for 800 volt. So that means the charger or DC bus are now using 800 volt will be quite common and norm now for new vehicle design. For existing vehicle design, it's too troublesome for them to upgrade the voltage. But for new vehicle design, we tend to use 800 volt as the normal standard. Because of 800 volt we're using or other voltage using, and my power point input voltage can be only a 220, 380, or 120, then we do need a power conversion. For the international standard, then we do need an isolated power converter to isolate for safety issue. Where power point in here, we get the power. And then when we deliver this power to electric vehicle, between them we need a transformer for the magnetic isolation. Make sure that this side of the circuit will not have DC connection directly to the other part of circuit to reduce the risks, reduce the EMI, reduce the short circuit issue as well. In case this winding is broken, short circuit, it won't affect the other side of the winding. So that is something safety concern. So that's why they do have an isolation requirement, like using transformer. Then in this case, you can see that if you want to reduce the voltage from high voltage to low voltage for the computer or for some low power devices, then in this case, we do need to have a step-down converter, reduce the voltage. Reduce the voltage from high voltage to low voltage, like 12 volt, 5 volt for the power computer, or even the wiper will be 12 volt. I mean, an electric vehicle, they're still using the conventional part, like the wiper, like the light LED, they still low voltage part, 12 volt, or maybe similar to this low voltage. In this case, they still need to reduce the voltage from high voltage a few 100 volt to about 12 volt to power up all the DC components. So that's how the DC converter are being used for an electric vehicle. So that's why this converter, if you want to reduce the voltage significantly, like a few hundred to about 5 volt, normal step-down converter not able to do the job properly, cannot reduce so much voltage. So what they can do will be using transformer. You see, I think you all heard about transformer. Just as I mentioned about even a charger, input side, they still have transformer for isolation. Transformer able to provide all this function, like the DC isolation, isolate between two DC side circuitry to have further protection. Can also reduce the EMI. You see, EMI is called electromagnetic interference. So that means some harmonic high frequency. We don't want that harmonic to go through your charging or go through the DC conversion system from one stage to other stage. We want to stop that. So once we use a magnetic isolation, then all this EMI can be stopped in the magnetic barrier. So this high frequency have difficulty. It still can go for a little bit, but not too much. Cannot go through to the other side. So that's why we need to have an EMI and barrier. So using transformer, we're able to do the job. So basically, you can see that, for instance, you got AC side here, possible transformer here. Then in here, we may have some converter here, or maybe charger. One thing is, you can see in here, this may create another pulse current. Then this pulse current may therefore transmit through here back to the source. Then you would make the power source become dirty. Because PG&E, your power company, do not like your harmonic in here. They hate it. So that's why they need you to say, because I need you to put a transformer so that your any EMI here will not transmit, will not contact directly to my power system. My power system from PG&E really dedicated. So they require you to put that. So that means nowadays all the charger system, you have by law or by standard, they somehow have a transformer inside. Many systems like that, even though your PV system, if you connect your PV to a power grid, you still need a transformer for the protection. So this will provide you a few functions, the EMI reduction, all the EMI can be stopped in here. And then you also DC isolation. Then you also provide a better transformation of voltage. The thing is, this voltage can be high voltage. High voltage. This voltage, maybe if you want to connect to a VCU, a computer, only 5 volt. So such a high voltage, you will still need a transformer to reduce the voltage. So this kind of the transformer built internally for the converter. Converter internally, they do a transformer internally. They can able to reduce the voltage. So that's how the technology is here. So they, of course, they are not using the big, huge silicon ion transformer. If you're using the charger or converter internal transformer, we are using a really high frequency transformer, which we can able to reduce the size by many times. Did I tell you the equation about the frequency relationship to the transformer? No? Okay. All the transformer, just like inductance, reduce the winding inductance. So inductance energy storage equal to half Li squared. That's the energy storage in the inductor. Have you seen this equation? Yeah. Then, but however, we are not using energy, we're using the power. So this is in the joule, right? But we are using kilowatt power. So power is equal to energy times the frequency. How often you get the energy from there? So that will say equal to half Li square F. Can you see my line? So now then, if using 60 Hertz, then that is the power, that's an inductance size. But if we don't use 60 Hertz, we use 60 kilohertz for the frequency for operation. Then this frequency really large, increased by 1,000 times. Then your inductance can be reduced by 1,000 times for same power level. So that means your transformer, if you use in 60 Hertz PG&E power level, but now we're putting into high frequency power conversion, power transformer, your transformer can be reduced by 1,000 times. That is wonderful, right? You can reduce the weight. So if you put a transformer into your electric vehicle, before will be like this room, but without 1,000 times, maybe this bottle. This real thing. That's what we're doing. That's the beauty for power electronics. Power electronics is technology, how to use the high frequency. So that's why today the charger, the converter, the motor is so small, so light, because we use high frequency. But you see from 60 Hertz, that's our main frequency, right? Now we use 60 kilohertz. But next step, we'll go to the megahertz. Now most of the converter we tend to go to megahertz, another 10 times, 20 times higher. And then next step, we are now, my research team working at 5 megahertz. So my student, I tell him, can your wireless power transfer work at 5 megahertz? Today he work at 1 megahertz. But by the end of his PhD should be 5 megahertz. Okay, that's the task. And then maybe you can help me to work with a motor, high frequency motor design. Okay. The things today we are all using low frequency motor system is useless. So next generation of motor will be high rotation speed motor. I can help you how to design a future motor, like the SR motor, high speed motor. They can be string the motor from that side become for the EV. That's our future technology. So we think about some research topic we can go for. We need to go for high impact research, not common research, not incremental research. You see, research, we got something called incremental. incremental. That means you just change a little bit. For instance, you design motor, today is 90%. Now you investigate, become 92%. You think, oh, I have done a good job. You improve by 2%. It's really good. But that's all it's called an incremental. Only some improvement. Your reviewer, other professors may say 2% is nothing. It's not important. So incremental research is this kind of the comment from all the other professors, other reviewers. What we need to do, probably not talk about 90% motor. We try, because this size will be, for example, like one meter cube. Now we can reduce 1,000 times, become 10 cm cube. So that is something we want to be a huge improvement compared to previous design. Not only in terms of efficiency, the overall performance in terms of size, weight, operation, safety can have huge improvement. Huge improvement, not only a little bit. So that's what we're trying to do. We call it destructive research. Something can destruct the whole entire research, not only incremental, completely disruptive. So that's what we try to do. High frequency power transformer was something we can look into to reduce most of the size of power conversion. Then for the electrical side, the major component you can see in the system, then we can see that, say, the DC battery system, the counter DC converter, they all are related to different kind of power conversion. They do exist in the EV system. Many DC to DC, DC to AC, rectifier, all this partially somewhere will exist in the DC bus there. And then you can see that the DC voltage nowadays in vehicle really high voltage. So how they design high voltage DC, also something we need to be careful. High voltage DC, we need to safety. We need to make sure that they're safe. The high voltage, we need to reduce it. 800 volt back to 5 volt, you see? 800 volt to 5 volt is not a simple job. So that's why we also need to be quite careful. You see all the sensors in the vehicle, like the camera, LiDAR, ultrasonic, they all work on 12 volt or 5 volt. So, but your DC bus is 800 volt. So how do you reduce the voltage? So that's something we need to also look into that. So we do have plans in the data center of orange color. I think I told you last week. So all the high voltage, we will code them, interleave them into orange color. And then all of them, we have a single DC bus to connect whole vehicle. 800 volt to connect all over the vehicle, from top to bottom, from front to the end. And then another major component, VCU, vehicle control unit. That's a jargon we use in electric vehicle, mainly just like car computer to control everything, you manage everything. So all the intelligence will firstly measure, sense, and go to the IC, the VCU to do the manipulation, and then make decision what next. And then you tell the motor drive what kind of torque, what kind of the motion is needed. And then because there's more than one motor, so the differential control motor will control the steering, control the movement, and how to overtake all this with the program in the VCU. So that means you have a driving profile, how to control your route. That will be programmed inside VCU, and then that will translate that requirement into the motion control. So that's how the VCU will do it. Of course, today we call that kind of intelligence. Before we put all the intelligence inside the VCU, but now that we found the VCU have oversubscribed, too much work to do. So we found a way to call the distributed intelligence. Some intelligence is not focused only on VCU. It's distributed to each of the major components. Just like our human being. Although we try to use a brain to process everything, but actually some of the intelligence we program in the other location of our human body. For example, like when you touch any really hot, then you withdraw your hand, because you don't need to wait for your brain to withdraw your finger from the heat source, because your reflex actually able to do that. So that's called the local intelligence. EV is like that. We need to develop local intelligence in each of the vehicle components to improve the control. So that's why VCU is now getting different kind of the new control method. like the local intelligence, the distributed intelligence, and centralized intelligence, how to relate all the intelligence to each portion. So, and then that are also related to the battery management system. The battery management system, they have own intelligence inside. They need to communicate with VCU to join them together. So they need to have coupling. So intelligence with the BMS and the VCU intelligence will connect together through some kind of the connection. So between them, we also have communication between different systems. So the basically communication channel, we are using Campus to do all the data processing and also all the control. So that's how the VCU shall look like. But temperature is also quite important. Temperature depends on your component, but you do need to control temperature for vehicle, make sure they are safe. Then typically most of motor, we are not able to operate a motor at too high temperature. I think less than 70 degrees will be quite a limit. Some motor we can able to operate at high temperature. The things motor are using copper winding. In theory, copper winding able to stand for high temperature, but that's not the case. All the copper winding, they got the coating, enamel coating, there's an isolation. That coating will break down at high temperature. Typically, it will be something like 125 degrees for some coating. And then you can choose some coating, even 200 degrees C if you like. But basically, most of motor winding, low cost one, will close to 120 to 150. But that's only for copper winding. The motor 70 degree mean you can see that when you test the motor, that is 70 degrees. But internally in the copper wire and most internally in the iron core, maybe even 30 degrees, maybe even higher. So that means 70 degrees is quite a limit because we know that internal temperature can be 30 degrees higher, maybe more. So that's why I set the limit to the 70 degrees. And then the best temperature, of course, will be room temperature, 25. Would be the best kind of format. Then that means if you want to have a high power motor, we need to have a forced cooling so that we're able to reduce the speed, even though the heat generation is really high, but we use forced cooling to reduce the temperature. The battery as well, most of lithium-ion battery, the operation temperature will be less than 60 degrees C. That's a law. So anything more than 60, it's not going to expose instantly, but give you a sign they will age really quickly, and they may expose to thermal runaway. Remember, thermal runaway for battery, lithium-ion battery, is not 60 degrees. But if external temperature is 60 degrees, internally can be 100, can be more than that. So that's why we set 60. Usually, you can check about the temperature thermal runaway for lithium, I think it's something like 150 or so, more than 100. So that means it's far away from thermal runaway, but we need to protect the battery from thermal runaway. The thermal management will also control the liquid. We have another pump, the pump for the motor or pump for the battery to maintain the temperature and also cooling fans. The liquid, if we use air cooling, we have cooling fans. But however, the cooling fan, we also need to cool the liquid somewhere in the evaporator. So that means the cooling fan will do the whole job anyway. So up to this point, any questions? They're quite straightforward, right? So the DC distribution, typically you can see that will be just like that. Many systems. Besides electric vehicle, we also have similar DC distribution, like electric boat or electric vessel or electric aircraft also use DC distribution. Many of ships have been using DC distribution for quite some time. Today, the so-called more electric aircraft concept or something more go to the all electric aircraft concept are using the DC distribution in the vehicle, in their vehicle, in the aircraft vehicle. So this concept is not new. Actually, for 30 years ago, we have been using DC distribution for many aircraft and electric boat. So that means the concept we use in electric vehicle already translated to all the other transportation systems. One reason is that the DC distribution can facilitate all the coupling, like the battery or DC, all the actuator, like the motor drive are actually DC anyway. we may use inverter like this. This at the DC voltage. So no point for us to put the DC because the motor is not running at AC. We're running from the DC source. So that means using DC distribution must the way we go for. So here will be electric vehicle configuration. So you can see that inside how they look like. Usually the bottom will be all our battery. So there, where we sit on there. So you can see that in case the battery on fire, then you're the first one to get in touch with the battery. But that's the lower level. And the front end and rear end will be the motor. So battery is the middle, and then this is the motor drive. If the front wheel drive is here, the motor will be here. Then transmission. Transmission means from the motor to the wheel. So here will be a little bit of transmission depending on the vehicle. If you use direct drive, the transmission will be really little, but if some transmission is do include the, for example, like the gearbox, so that would be some gearbox there. And the battery, inside the traction, the huge battery here, we still need to have auxiliary battery, a small battery. That will be similar to our start battery for our vehicle. We still maintain a 12-volt battery here. We don't only rely on it, so these two are separate. So although we do a charger from here, we charge to this battery, small battery 12-volt. This battery mainly to provide the basic operation, most of basic operation, like the computer, like some wiper lighting or this kind of thing. To continue the charger from the main battery, they separate them into two different places. That's mainly for safety, and also we try to maintain a constant 12-volt to provide all the basic control system for the vehicle. So that's how a typical EV configuration look like. Then for the DC power conversion system, then not only the battery we need a DC power converter. You can see that today we do have a lot of the fuel cell vehicle, like hydrogen fuel cell. Hydrogen fuel cell also a DC power source. So hydrogen fuel cell, although may not able to provide high instant current, but still are really good stable DC source. So this DC source will of course we need to connect them with a battery or supercapacitor in the DC link. The thing is, fuel cell is impossible to have power regeneration through the hydrogen fuel cell. The hydrogen fuel cell can only give away the energy. In case the vehicle is braking or decelerate, the energy needs to be absorbed by the battery or the supercapacitor. So that means even though we use the fuel cell for the vehicle DC bus, we still need to put some battery there, a little bit for the startup, stabilize the system, and also power regeneration. Then, beside the DC bus, we also have the data bus. Some of the vehicles, they may match the DC bus and AC bus together. Some of them, they may using the bidirectional power flow also provide the data. Of course, for the today vehicle, we don't need to do that. We can able to separate data bus to do all the communication. So here will be one of the picture. You can see some of the configuration where each component. So this is the vehicle I developed myself 20 years ago. We sold this vehicle to the market worldwide, including Hong Kong, China, Singapore, Malaysia, US, and Europe. So we sold 1,000 of this. So you can see that when we start to sell this vehicle 20 years ago, there's no Tesla, no BYD, no Leaf, no BMW i3. So we are the first one of people to develop a commercial EV system, not only in research, but real vehicle. So let's really to look into with the BMS. You see, BMS is, I have been talking about BMS for many times. It's so important because the most expensive component in a vehicle must be the battery. Much more expensive than the motor. Motor is not expensive anymore. It is small size, but the battery is the most expensive. And the motor don't have that much aging as compared to battery. A motor actually, to use them for 10 years, 20 years, is not really difficult. I think, for example, you can see that many motors in a factory, maybe in your refrigerator, right? Then you seldom need to replace the motor inside your refrigerator. Even after 5 years, 6 years, you don't need to have that problem. But for EV, it's the same. You don't need to replace the motor. But however, the battery do have the age. So usually about around 7 years. Some of the good ones maybe 8 years. So most manufacturers only guarantee for 4 years. So that means we need the BMS is something going in the motor system, the battery system, to make sure the battery are working well, including all the protection, SOC and SOH management. The charger itself is not the BMS. Charger only inject energy to the battery system. Inside the battery system, we need to have separate BMS to do. So that means don't mix up all that. So we have charger. Then you go to our battery. The battery inside also have BMS. We integrate into each of the battery cell. So the charger will select what kind of current go into the whole system. The battery system itself, they have internal BMS to check all the current condition, the battery condition to do the job. So it doesn't care about what kind of charger you're using because they say this charging are for what kind of the charging standard. Usually EV, I think the next few lecture will mention about the charging standard. So we just work the battery along with some international standard, then they should be okay. But internally BMS, the BMS battery management system is trying to work with each of the battery cell properly. Control its safety, control its current, control the state of charge, state of health, temperature. So that means this BMS need to calibrate properly with the battery. You can't just go to some shop to buy BMS, some shop to buy a battery and put them together. No, it doesn't work this way. They need to integrate together internally before ex-factory. So that means you need to calibrate it properly. So BMS will be also able to help you to determine the state of charge, state of health. Do you know this term, state of charge? I think you all know. State of charge means how much energy, state of health means the healthy condition. A new battery, 100% state of health. A lousy battery after using a few years, become 80%, maybe 70%, then you need to change. And then the charger is AC converter. AC converter is only a charger, it's not anything with BMS. And then, like many converter, you can use it. For example, like fiber converter, HPH converter, you can use it. Then for low power, we use fiber converter. Is a name for the converter system. And then BMS is something you need to use internally with the battery to do all the duty job. So for powertrain design, there's a many requirement or design method. We can use them for the powertrain design. As you see just now, our powertrain design got many different topology because we got the battery, we got the charger, we got the motor, then we may have the gearbox, the drivetrain. How to arrange them will be something is your design duty. So that means firstly, we need to look into the topology of the powertrain design we need to go for. Because as I mentioned, there's many different arrangements to put them together. We call it topology. So like how to put all these components together in your vehicle. So that topology for vehicle. And then component topology. Then once you do the system design, then you have a component level. How to arrange the components together. Each of the parts, you may have their own component. For example, the battery. You may need to think about, I use one battery or two batteries in parallel. You can buy different battery pack into a system. That's down to component level. And then for the motor as well, then you have different kind of the motor selection. Then you can select different kind of motor. So what kind of motor? You use SR motor, industrial motor, or SR DC motor. Then there's a component level. Of course, the next thing is the component size. Then you may need to think about, I need 100 kilowatt motor. But in the market, we got this big 100 kilowatt, and also this big 100 kilowatt. Which one I shall use? For this smaller one, I need to put in forced cooling, liquid cooling. For this one, only air cooling. So which one shall I use? So that's a selection about the component sizing. Which one you shall use? This one will be cost you maybe 100,000, but this one cost you 500,000. Because they use better technology. So that's the thing you need to think about that. The component sizing you need to use. And then you also need to think about overall powertrain control. The whole powertrain would relate to the modeling method, how to model the signal across the powertrain, how to control the torque, how to control the speed, how to control the safety. All these kind of control mechanisms are embedded inside the powertrain. So these are 4 criteria for to design the vehicle. Powertrain design will be needed for your development. Okay. So that's why just the powertrain design, we've got many considerations in here. Then we also have something called the design objective when we design powertrain. Design objective means we need to optimize the performance, optimize the efficiency for the whole system. And then, of course, we need to look into the safety and the overall user experience. User experience means we need to make sure the design will be good for the user. So that's to say, when we firstly design EV, you try to make the EV really much look like a gasoline vehicle. The control are the same. When you sit on vehicle, it's blindfolded, you may not know it's an EV or gasoline vehicle. So you may make them feel exactly the same. That's how the initial user experience we tend to like. But gradually, we think we need to change because we know that for EV and user experience, getting more aggressive. They like high performance. In this case, they may like to have, for example, like how to make the EV become more energy saving. Then in this case, they may eliminate the idling for the vehicle. You see, gasoline vehicle, when you don't press the gas, then you still have some idling movement. The vehicle will not stop, and a really small movement. But for EV, it's not the same. When you release the gas, then you just stop because they want to improve the efficiency. So that means the design for the user experience point of view, they need to fit the new requirement. So there's many different things. Some people, they think the EV is too quiet. They like to put some sound, some noise there. When you press the gas pedal, you can feel this kind of sound. But some people doesn't like that. So there's many user experience we need to include it in the design. Even though when we do the steering and vehicle control, we need to, when the vehicle is driving, how many space between the vehicle will be needed compared to front vehicle. So we have many kind of the speed requirement or safety requirement can be included in all this design. And all this design can be programmable. So that's something we like to have. And also environmental issue, we also need to think about in all the design objective. Environmental issue mean, for example, how your vehicle can make it more environmental friendly. Like, can your motor, at the end of the day, can be recycled? Can your battery become recyclable? So, and also lastly, about the scale. So can your design can be scalable? Can be one design for this power level, you can scale up, scale down to other power level. So that's all the design objective. The thing is, when a vehicle manufacturer, they design one vehicle as now, then for next few years, they need to upgrade the model. They may need to scale up, scale down to other type of the design. So that means the design is scalable, then that will be much easier for them to go to the next generation and next version. So that's why scalable design will be also important. Then let's go for each one to discuss that. So energy efficiency, of course, is one of the most important part for all the powertrain conversion. So including how we examine different part of the power conversion, because so many power conversion systems there, including the motor, charger, DC conversion, and many of them we do have different kind of the power loss requirement. So this will highly relate to how we control the range of the driving, how to reduce the energy consumption. So that means the design objective here, how to optimize the efficiency is something we need to look into. That may highly relate to the cost of the material, cost of the motor, cost of the battery as well. Some batteries, they have low efficiency. Some batteries have high efficiency. Some batteries 99%, as I mentioned. Some batteries only have 95%. So which one you go for? That within the 5% of energy performance, but that also relate to maybe 100% of the cost. So that's the decision you need to make. And also range optimization, how to optimize the capacity and the weight of the vehicle. You see a vehicle usually today, many vehicles can run for 300 miles. That's quite a standard norm. But if you want to increase the vehicle range to say 400 miles, maybe 500 miles, then you may need to put more battery there. So that means when you put more battery, additional cost, additional weight. So that's a pros and cons. So you increase the performance today, you're quite okay by putting more battery, but you can also increase the overall weight, overall design, and also the changing the inertia. So that is that kind of the comparison you need to make when you do your range optimization. But probably in the near future, when the charging is much better, you can able to have high power charging, say 5 minute, 10-minute charging, and you don't need to put that many pieces of battery system. Then you can reduce some of the battery there. So by the way, today, do we have any presentation for the mini project? I didn't look at the chart, but I know some of you already presented, so we don't have other presentation yet. Okay, then I continue. Another important design criteria is the acceleration and the performance. Many EV users, they enjoy the EV because of the acceleration, like 0 to 1,000 km per hour. I think we did that tutorial. Then why? And we try to reduce them. The best vehicle in search for market will be 1.83 seconds, right? So I don't think any vehicle can less than that. 1.83. I think, did you see my answer for the homework one? Yeah. 1.83 only when the friction coefficient go up to 1.5. You can able to have 1.83 acceleration time for 0 to 100 km per hour. So I don't think any vehicle able to be less than 1.83 seconds for that acceleration. So that is also the limitation for the acceleration. Yeah. So if in the future somebody sell your vehicle, they say my vehicle, the acceleration from 0 to 100 km per hour is 1.5 seconds or 1 second, impossible. That's beyond the physics. Impossible. Then we know. But anyway, come back to here. Then the acceleration, then you can see most of vehicle, good vehicle may something like 3 seconds, 3.3 seconds. That kind is quite long, quite common. So if you design vehicle, you think about your acceleration and the performance. Can you able to have an instant, we call it the standstill torque, or it's called the start-up torque, able to perform the full torque for you to speed up the vehicle. So that kind of the response time also quite important because it relates to when you press the gas pedal, then the delay must be minimized. So from the pedal, then you tell the VCU, we need to speed up the vehicle. VCU will tell your motor driver. Motor driver will control the voltage and current to the motor. Then the motor will go to the wheel. You see, there's a lot of the delay there anyway. So beside the delay, then we need to speed up the performance, or the delay must be reduced. And then we need to have a sufficient torque to appear on the motor in order to provide that acceleration performance. So this loop must be responsive and also smooth. Otherwise, if the acceleration is really pulsation, then you don't have any smoothness. So that's something we need to look into. And then regeneration. Regeneration is getting more important nowadays because the good performing vehicle, we need them to have really good power regeneration so that any energy in the braking or going down the hill can be returned to the battery. But usually a motor, we have 80% efficiency or 90% efficiency at 95. That can be quite common for motoring. But for power regen, a motor may not be designed good in the power regeneration. So that means if you want a motor to have a good performance, you need to tailor-make or try to design a motor which side you want to more performance, motoring or efficiency. Usually total add together cannot be more than 180% efficiency. So you have a 90% there, then you may have less than 90% in the power regeneration. May sometimes only go down to 70% or 80%. So that means both adding together, we have difficulty to have high efficiency for both ends because you can't design motor perfectly. Just like when we design the SR motor just now, with motoring and then regeneration. So the motoring, we can design really nice motoring, but we can also design the regeneration perfectly well for the inductance profile. So we can't have perfect for both ends. So motor design will be like that. We need to try a system so that power regeneration is also good, but we can't make both motoring and regeneration to be also perfectly good. All the vehicles we tend to have compact and lightweight, so of course that will be a major requirement. So how to do that? Probably all the things will go to the battery and also the motor system. As I mentioned, battery, we can use high-speed motor, good cooling system. We can reduce the motor size. That's something we have been using it. And then for the battery as well, that battery, we really careful about the temperature. If we overrate the battery, then we may have high temperature in the battery. Then we need to have really good cooling system. So don't underestimate many of the battery system in a vehicle. They do use a liquid coolant to reduce the temperature, so that in case anything, you can able to power up the battery to high current, charge and discharge. You can also, that means when you charge the battery, say 30-minute charging, then the system already have a good cooling system, cool down the battery to assist you to have high-speed charging. Otherwise, the charging getting really hot. Just like when you're charging a phone, sometimes you get quite warm. Why is that? Because the charging will have a lot of the power losses. Because you try to inject high current to the battery, the chemical reaction will generate a lot of the side effect like the heat. So that's why cost optimization will be important. So you need to think about how to make it the compact size and lightweight by using the method we propose. But that will, therefore, with the cost implication, because you need to add on the cooling system, add on the maybe expensive motor, maybe you cannot using normal copper wire, you use more special type of wire, even though the motor metal core, you need to select those really low power loss core. For example, like you don't use powder iron, you may need to use a really good high nickel type of the flat wire to make the motor. So in this case, you can make the motor become really low losses, but expensive. So that's the cost optimization, how you balance the performance and the cost, and also the technology. So that's many items we have design issue here. Up to this point, any question? I think it's just me to do most of the talking, right? And next few criteria will be the reliability and the lifetime, right? Vehicle reliability, I think, is most important. So without reliability, it's not a vehicle anymore. So how to make it reliable? I think the main thing will be how, firstly, the battery must be reliable, motor must be reliable, and the control must be reliable. All of them must be reliable. And then to do this one, then you need a really good sensor, so that you can control, you can sense the environment, sense all the conditions to control your motor, control your driving. So that means reliability related to all of them. Without sensor, I don't think you can make something really be reliable. So usually we don't need a really good system. If you buy a perfect system, very reliable system, also be okay. But however, if you spend less money, but you input more control feedback, you can actually improve the reliability of your whole system by putting a few more sensors. So that's another way we can improve the reliability, and also we can therefore improve the lead time. And so that means the design consideration including how to make the system robust. Like the motor we try to use, we tend not to use DC motor, tend not to use industrial motor, we tend to use special DC motor. And to reduce some multi-phase DC motor, then each phase can independent control. Or we tend to use SR motor. So each phase has independent control, then we can have higher reliability for the motor. And then for the battery, then our battery design, we may need to think about the battery using series and parallel. So in case anything happens, one string is broken, we still have another string to operate for the battery. If all the battery cells are only connected at one string in purely series connection, in case one battery is broken, you have no alternative. Your vehicle needs to shut down. So that means even the battery design, you have some method to give you the more flexibility in terms of the safety and the reliability. And then another design will be for powertrain system. Today we design the scalability, how to scale them. Also talking about in module design. You see the vehicle today, the whole vehicle are designed in power module. If open a vehicle, you do not see too many components. Only a few boxes there, a few compartment or enclosure. Because each enclosure will be one power module. Now the motor is come with the whole motor module with the inverter. Inverter module packaging in the same kind of the configuration. And then you got battery there. Your battery, you can't see anything inside the whole big package with a really strong metal to protect them. So you can't open up. When you change the battery, you need to change the whole chassis, the whole battery pack. You can't do it yourself. You need to go back to the manufacturer to change it. So the motor as well, this is not changing the motor brush. You can't change the motor winding. The whole package, including inverter, you need to change it. So that means you also have some other control box and other sensor. So for EV, everything become a modular approach. You couldn't do anything to fine-tune, adjust some component. We don't need to do that because to get somebody to repair is really expensive. And then for manufacturer point of view, they will have a lot of this component available. And in case you need to repair them, you just swap them. You see in a manufacturing plant, usually if they recruit another manpower or engineer to repair your vehicle is really expensive. So what they're trying to do will be they will manufacture in more than they needed. For example, like in this batch, they try to produce 1 million vehicle. And then they don't produce 1 million, they produce 1.2 million. So 200,000 will keep in stock, not going to sell, but only for spare part and replacement. Then in this case, so that 200,000 can go for maybe 10 years also. In this case, they don't need to reserve a manpower or system to repair it. Because get somebody to say, get you to repair an EV, then you cost them maybe $1,000 per day. It's not worth to do that. If they got many spare EV, this motor broken, take the motor from there, just swap it. Because they got stock there. So they use this method for repairing. They don't actually going to repair your vehicle. They only use modular approach for replacement. They don't even spend any time to look into the problem, why it's broken. They just replace it. So that's the way we try to maintain the vehicle, to use modular approach to do everything. So when that stop is all finished, the whole series will be stopped supporting. So that's why here the manufacturer say, no, this series we're not going to support you after a year, because they finish all the stock. They're not going to support you. So you need to find your way to fix your vehicle. So that's how they're going to do in all the manufacturing part, all the maintenance. And then number 9 and 10, the thermal management. So thermal management is another important area for to look into a vehicle. I mean, the major issue for vehicle, of course, also go into thermal things. Thermal management relate to all the power components have a heat generating component. Because whenever there's a current pass through a copper wire, you got power generator, and then when magnetic field go through your magnetic core, then you got magnetic power losses. So all these things, the battery with the current pass through the chemical reaction, then you got the heat generated. All this will generate heat. We need to keep removing the heat in order to maintain the temperature of the vehicle. All the components today we see in a vehicle, the best operation temperature, also room temperature, say 25 degrees C. So include the battery and also the motor, including PV. PV is not, you see, a PV panel, if you're under the sunshine, the temperature can go up to 60 degrees C. The efficiency is really poor. So we need to cool down the PV to 25, 20 degrees. Then the efficiency of PV can getting better, close up to 24. The efficiency of PV is 24%. If you heat up to 60 under direct sunlight, the efficiency may drop to 15%. percent not worth to do that. Motor will be a similar situation. If motor good efficiency 25 degrees C, but if you raise the motor to high temperature, maybe under the high power, you go up to 80 degrees C, the efficiency of the motor will be really poor. The torque will be degraded. You cannot able to provide full torque, only provide 80% torque, maybe 70% torque. So that's why thermal management for this kind of the motor design will be so important. And then we also need to think about integration vehicle control unit. Each of the component in the vehicle, they do an IoT for the information. They also have a connection to the VCU so that all the data can communicate. Today, we do have a standard for each of the vehicle component. They were compatible with your own vehicle VCU, so they communicate with the campus. But the thing is, campus is not universal regulated. Each of the EV company have their own prototype for their campus. They may use this field bit for your information, this field bit for control, what kind of frequency, what kind of pulses. They all different from different manufacturer. So there isn't any international standard yet. So it all depends your own company, how to use the campus, how to program your own prototype. So that means this company's motor cannot use for the other company motor because they are not compatible. The motor itself maybe they are the same, but when they program them with the campus, they become different. So that means how to compatible between them, how to work with the VCU also quite different. So that's why it highly related to your software development, how to optimize control, and all the intelligent control relate to a lot of the VCU control system. So that highly related to your safety, performance, optimization. So that means at the moment they all are quite different. Just like your phone. Your phone, if you use Motorola or Apple or to use Samsung, they're all kind of different. You can't mix them. They all using different kind of protocol. So like EV as well, BYD EV, the motor, although it look really much similar to the Tesla, but you can't mix them. The control is different, the charger is different, everything are different. You don't have any way to put them together. So that's why today, when you go to a charging station, some chargers are using European standard, some are using the NCAS standard like Tesla standard, some of them using the China standard. Yeah, so they all mix. So that's why some of the building, if they want to accommodate for many different chargers, they may put more than one charging outlet, one for the Tesla, one for the European standard, one for the Japanese standard, one for the China standard. So really confusing, wasting the money. And for design, more importantly, will be the user experience. The vehicle design will ensure that the user will feel happy about it, can able to enjoy the control, enjoy the driving. How to design a vehicle so that you can meet with the user experience will be so important. That including performance, easy to use, and how to transit from one vehicle to other vehicle. All the control and button look quite similar, cannot be deviated by too much. At the moment, all the EV, the transition will be, they try to make all the EV transition from a conventional vehicle to EV, but the control doesn't change that much. But gradually, we can still see that changes now because some of the buttons can be eliminated, like the autonomous vehicle in the future, when we don't need the steering wheel, we don't need the gas pedal, right? Maybe only one pedal. The thing is, one pedal, when we release the gas pedal, it just stop the vehicle. So in theory, you don't need a brake. You don't need the gas there. Only one will be enough. But for commercial vehicle, we got the gas pedal, we got the brake. So that's why we still have two. But in the go back to 20, 30 years ago, we got the clutch, right? You got three pedal, clutch, brake, and accelerator. But now we only have two. But future, we only have one. And then the next future, we don't have any because autonomous vehicle. Next future, without steering wheel, nothing. We just sit there. And then maybe in the future, we use brainwave to control the EV. But that's quite true. We are now researching how to use the brainwave. We have been using the brainwave to control some motor and wheelchair. That will be quite successful. So next thing will be using the brainwave. The brainwave are really small signal. We can amplify it. We can put something in here, amplify the signal, and connect this device to the vehicle. So it's now doing it. So hopefully something come up in next few years. If you follow me to do a PhD, then I can show you how to use the brainwave control the vehicle. That's something really, really, really interesting. But anyway, so environmental impact, I think all the vehicle, we must fulfill the environmental impact. Why is that? If a vehicle after 7 years, the battery getting too old, you fall to the landfill. That's a such waste. At the moment, all the vehicle battery, you cannot recycle because the manufacturing of battery, they tend to use the lowest cost method to do that. So that means the lowest cost, that means they cannot recycle. When end of the day, they just cannot recycle all the material like the nickel, lithium, all the expensive material cannot be recycled. That's really not environmental friendly. So that means in the future, many green group, environmental friendly group, they think about, can we make the vehicle design in such a way to be recyclable? That means the battery, rather than put in the dump site, landfill, we can go to the factory using really simple mechanism, we can recycle them. At the moment, all the battery, you see there are two polarity, positive and negative, and on electrolyte, and also the separator, they use some plastic non-organic glue to put them together. So this glue can make them not able to recycle because this glue is oil-based. We cannot separate that. So that's why the end of your problem will be all the things at end of life, we cannot separate all the components. So today we got another new technology which we use water-based adhesive. So that means we are able to use very simple method like heat up and put them in the water. We are able to recycle all the material, but they are very expensive for the manufacturing. So that's why people think about which one they should use. They want to reduce the initial cost, or they want a more environmental friendly. So, but however, because this issue, many new government, they may think about in the future, they impose heavy tax on those items cannot be recycled. That means if you put your unit into the landfill, they may charge you expensively, heavily. So to compensate for all this recycle research development. So that means when you design EV, although we don't have too much impact at the moment, but I think in really near future, I think environmental impact and sustainability will be so important for all the EV design, including battery, motor, control system, computer, IC design, and also even though all the enclosure, the body design, and suspension, everything will need to be included. So let's think about, for all the design, what other area can you think of? We have discussed about 12 points, right? For the vehicle design for powertrain. Which part we haven't touched? We haven't thought about that. Maybe that's a good question in the next midterm exam. I think next Thursday you're going to midterm. So we're going to pick, I think we're going to do it on the canvas. Then probably when you come here, then I'm not here. Sorry about that. I got another important meeting. So you try to open a canvas and then do your midterm here. After 2 hours, then you can go. And in case the canvas is not working, there may be somebody chance 1% the canvas is not working. I will prepare some paper copy. In case anything happens, I will pass to my student. The envelope will seal that he can't pinch it, he can't watch it, what's inside. At the time, 1:30, he will open up. In case the canvas is not working, he will open up the envelope and then pass to you. Okay, he's my student, so I can ask him to help me. But I think canvas should be working. But anyway, here, what other powertrain design you think will be we need to consider? What do you think? It's very, you don't have any fixed answer. Can be anything, right? So anything that can be important, can be next design criteria. Yeah. Something in here, we're saying, I think we do have an autonomous vehicle now. So that means once we got autonomous vehicle, then in this case, we need to look into how can autonomous vehicle modify the powertrain design. And also in the future, we may have the smart office, smart car. That will be how to modify the powertrain design. In the future vehicle, when you have autonomous, your vehicle can be your office, mobile office. And then you need to prepare for future upgrade. Once the powertrain there, if you cannot be upgradable, it's no use. So we need to think about future upgrade or cost wireless power charging. At the moment, 100% vehicle don't have wireless power charging, only for research. But how do we develop wireless charging in the next few years? I think it actually will become real and practical happening for all the vehicles, but how that can be done. If you go for these 4 items, what kind of the future development for powertrain we need to look into, right? So I think we do have some answer here. We don't have too much time now. You can go through them. We can discuss next week. Okay. Any question up to this point? We do have another 4 questions for the homework, right? So, and if you finish earlier, then I can post my answer early. All my homework answer will be really similar to the midterm. Our midterm will be open book. So you don't have to worry anything about anything. So our midterm will be open book. So you can refer to anything, but don't refer to the internet. Try not to. Yeah. Although my answer will not appear in the internet, it's my private question. But however, using internet to answer, using ChatGPT answer is not that nice, right? I want to see your own thought here. Okay. So Thursday next week, the midterm here, then we try to look into all the different. The exam of about 1 hour, 15 to 1.5. Yeah. But you can finish earlier, you can go. Any question?
Oh, when is the midterm?
And we have Thursday next week.
Next week, Thursday?
Thursday, 1:30 to 3:30. Here. And the canvas, I try to use canvas. So then we answer all the questions in canvas. We remember to bring your own computer. Yeah. But in case anything happens, we still have the second and insurance, we still have paper copy just in case anything.
Yeah, I will be in South Carolina during that time.
Okay, can you still open up your computer to do your internet?
Yeah, I can, but
Please.
I have to use, maybe that, I mean, timing might change.
We try to, because you tell me you may not be on time to do midterm. I know your name, so in case your time is different from others, that will be okay. Yeah, because you're not in the town. So that's okay. But the other one, try to do it from 1:30 to 3:30. Because the camera will tell me about the time you enter into exam. Right? The exam will be really similar to homework, similar to my lecture. All your lecture in your computer, so don't worry, they're all there. My duty is try to help you understand to get higher mark. My duty is not give you low mark. My duty is try to find the best way to give you high mark, try to give you an A, right? Okay, that's all. Okay, see you again on Thursday again.